Thank you, Lyman. So let me again thank the Shaw Foundation, thank the university, and Hong Kong for welcoming us here and giving us a chance to spend some time here, meet folks here, and talk to you about what we've learned from our observations in the microwave background. So the goal of my section of the talk, the final section, is to give you a sense of what we've learned about cosmology from these wonderful observations, and what is the picture that emerges from what we've seen. And the picture that emerges about the universe is a universe that in some ways is remarkably simple. It's a universe in which the laws of physics that we've learned on Earth, laws of physics that you're learning about in school, are valid on the size of the universe. It's a universe in which general relativity, this idea of Einstein, is valid on the size of the universe. It's a universe, remember back when Chuck talked about Friedman saying there are all these different possibilities out there. Things could be really rich and different, which is what, when I studied it, I thought would be out there, something very complicated. What emerged is from our data, emerged from measuring the size of those hot and cold spots that Lyman talked about, is a universe that's very simple. The geometry of the universe is flat. That means that the Euclidean geometry, the sum of the angles of a triangle, is 180 degrees, that many of you learned in middle school, is valid not only on a piece of paper, but on the size of the visible universe. Such a flat universe has its total energy equal to zero. The energy in expansion is exactly equal to the energy in gravity. It's a universe, it turns out when you look at those fluctuations, and as Lyman showed you, we see tens of thousands of hot and cold spots. We look at 1 million independent points on the sky. So we're making lots of measurements of what we see. The statistical properties of those fluctuations could be summarized really in just one number, an overall amplitude, and for a little more accurate, an amplitude and how it varies with size. So it's a universe, while it could have been very complex, turns out to be really simple. Geometrically flat, total energy zero. The fluctuations are what we call Gaussian. They're drawn from a bell curve distribution. And the fluctuations, these tiny ripples, are really the simplest they could be. While the universe is simple, this early universe, it's also in some ways strange because of its composition. What's emerged by looking at the properties of these fluctuations is that the composition of the universe is odd. Atoms, the stuff in the periodic table, the stuff that makes up us and the chairs and everything we see around us, turns out to make up only about 4.6% of the universe. That's a number that we've measured with precision by looking at the pattern of fluctuations. That's one of the things we've learned from the detailed analysis of the experiment. What's odd is 95% of the universe is something else. Not only that, it turns out to be, as far as we could best understand at the moment, two different something elses. One part, and again, this is a number we've measured well, is what we call dark matter. That makes up about 23% of the universe. That's stuff that behaves like ordinary matter under gravity. The gravity affects dark matter and atoms the same way. The difference is atoms interact with light. They interact with us. We can touch them. This dark matter, as far as we can tell, doesn't interact with light. What is this dark matter? We don't know. All we can do is sense it gravitationally. Perhaps some of you, and I see there are many students in the room here, will be among the people who figure out what the dark matter is. And there's lots of experiments that are looking for it now. The rest of the universe, this is associated with this acceleration that Chuck mentioned, we call dark energy. There seems to be energy associated with empty space. This stuff, whatever it is, doesn't even interact with gravity normally. It just seems to fill empty space and doesn't fall into galaxies, doesn't do anything else. So this is our picture of what the universe looks like today. Simple, but in some ways very strange. When we look at the microwave background, when we look at this leftover heat from the Big Bang, when we looked at this balloon that Lyman showed you, something to remember is we're looking back in time. Because light travels at a finite speed, as we look out in space, we look back in time. We see the sun as it was 8 minutes ago, Jupiter as it was 30 minutes ago, because it takes light 30 minutes to get from Jupiter to us. We see the nearby stars as they were 5 years ago, 10 years ago, perhaps 100 years ago, depending on the star. That's, of course, symmetric. If you stood in orbit around a nearby star, say you were looking at a star 20 light years away, living on that star, you'd look at us, you'd see us as we were 20 years ago. You'd observe me with a full head of hair. The further out you go, the further back you go in time. We see nearby galaxies as they were 1 million years ago. When we look at the microwave background, we're looking at the oldest light in the universe. Most of the light we see, most of what this radio antenna, this TV antenna that Lyman talked about detects, is light that's been traveling for 13.7 billion years. It's light that's coming from when the universe was about 380,000 years old. Back then, the composition of the universe was different. Still lots of dark matter, some atomic matter, a little bit more, up to about 12%, but also lots of radiation and lots of neutrinos. So to talk about that, let me just remind you of the history of the universe. Our universe starts out very, very hot and dense. As it expands, it cools. And when we look back to about 300,000 to 400,000 years after the Big Bang, we're looking back to a time at which the universe got cold enough that electrons and protons combined to make hydrogen. Before that time, there was just a plasma of electrons and protons. What happens 380,000 years ago, that makes that the special time we see. It's that when atoms first form. Radiation does not interact that much with atoms. It's like the room becoming clear, and light can propagate from then to us. So that's what we look at when we see the microwave sky. So to give you a sense of what are some of the questions we looked at with WMAP, what are some of the things that emerged, is when we look at the universe today isn't uniform. Things look lumpy. There's galaxies, there's stars, there's planets, there's us. Yet the early universe was nearly uniform. How did that change? Why is the universe lumpy? What generated these fluctuations that we see in the sky? What are the best ways of understanding what could be there? Why is something changing over space? These are the kinds of questions that I and many of my colleagues thought about in the time leading up to WMAP. Unlike my colleagues, I'm a theorist. I don't actually build anything. I'm not allowed to touch anything. They never let me touch any component of WMAP. That's why it operated so successfully. My role is to think about what we can learn from the data and think about some of the questions that help motivate it. So the kinds of things we thought about are, could these fluctuations that grew to form us, what do they do to? Could they be variations in density? Could that part of the universe have more matter, that part less? Is that what those fluctuations we see in the microwave sky, is that what's going on there? Or could they be variations in composition? Maybe the density of the universe is the same everywhere, and what's changing is over there there's more electrons and fewer photons, and over there there's more photons. So the composition changes from place to place. We give these names adiabatic and isocurvature, and they're just an example of some of the different ideas we think about or have thought about for growth of structure. And when we go back to the 1980s, the 1990s, before we had this experiment, we debated about these different ideas, and they were competing thoughts on what might be there. But one of the many things WMAP did was, besides just measuring the composition of the universe, we tested these ideas on where structure came from. So to give you a sense of how this works, let's start with variations here in the composition of the universe. In this case, we've got More photons here, less photons there. This gives rise to a prediction for this fluctuation spectrum we've talked about. So let's focus on the top one here. These are measurements of temperature as a function of scale. And you see there's a pattern here in which there are 2 bumps here and not much there. One of the most important ones is, in this case, is looking at polarization. Light is polarized. Light consists of electromagnetic waves. And the electromagnetic waves can propagate towards you with the electric field going this way or going this way. The reason you wear polarized glasses is to separate the different polarizations. WMAP doesn't only measure temperature. The detectors also measure polarization. And we can look at the pattern of temperature and polarization. Models in which you have, variations in the composition of the universe predict a positive signal for temperature and polarization here. On the other hand, we can look at models in which the composition of the universe is the same, but there's more density there, less density there. Those models predict a different pattern of peaks and predict a negative signal for temperature and polarization here. So this shows how measuring these kinds of signals tells us about what the variations were like in the early universe that gave rise to galaxies. And here's our measurements of temperature. You've seen this plot before. You can see there's one big peak, so the temperature pattern. And here's our temperature polarization pattern. Notice this is negative. It's not positive. Just from seeing that, that tells us the fluctuations that grew to form galaxies are variations in density. The composition of the universe is the same over there and over there. There are no significant variations in what type of stuff is there. There's just more stuff in different places. This tells us when we look at our picture of the sky that the fluctuations we see are density variations, with the cold spots reflecting regions that are lower density, the hot spots on these scales regions that are higher density. So that they're not composition variations, and that tells us where structure comes from. Once we know the nature of these fluctuations, we can ask, how can we fit this kind of data? And the way we fit this data is by varying the basic component properties of what the universe is, because that's what determines the properties of these fluctuations. What determines this pattern of peaks here, what makes these bumps and wiggles go up and down, is what the universe is made of. If the universe had more atoms in it, this first peak would be higher, the second peak would be lower. So by measuring the ratio of these peaks, and you can see the WMAP measurements have measured them with precision, that's how we know the density of atoms is about 4.6%. Lyman already mentioned by measuring the peak position, the size of the hot and cold spots, that gives us the age of the universe, another key component, because that determines the geometry. You can think about these spots actually being the distance the sound wave can move in the age of the universe. We know how big the spot is. You move it further away, they get smaller. Someone holds up something, moves it further away, it gets smaller. Smaller it is, the smaller the angular scale, the curve would have shifted this way. So by measuring this position, that gives us the age. The density of matter determines this overall structure here, so we can measure that as well. And here we go. So here's just going over this again. How do we measure things like how many atoms there are in the universe? You increase the number of atoms. The curves here show what happens. You increase it by 10, 20, 30, 40%. First peak goes up. Second peak goes down. Lower it, goes the other way. How about what's the density of matter? Increase the density of matter. First peak goes down. Second peak goes down. Third peak stays the same. So by looking at these ratios, you can study what the composition of the universe is. Well, that's what we did. And what to me was truly remarkable is how such a model with so few parameters can fit lots of data. We have 1 million measurements on the sky, and all those measurements can be fit by these basic parameters. The first we've already talked about, the age of the universe. We can now say with some confidence that the age of the universe is about 13.7 billion years old, with an uncertainty of only 1%. When I was in high school and even in graduate school, people argued, is the universe 10 billion years old or 20 billion years old? And there was really no accurate way of measuring it. We now can say that. We've measured the density of atoms quite accurately. If you're sitting in an average place in the universe, the density of atoms is 0.26 atoms per cubic meter. So every cubic meter, get a little bit less than an atom. You can do the math. 4 cubic meters, you get 1 atom. That's a number we've measured with about 2% uncertainty, because it comes right off of that ratio of those peak heights. And you've seen we've measured those things, the amplitude of fluctuations, the function of scale, quite accurately. The density of matter, that's about 5.9 times the density of atoms. That's strange. If atoms were all there was, that number should be 1. The fact that we've measured that ratio and it's different from 1 says there's a lot of stuff out there that behaves under same kind of gravitation. It weighs something, it has gravity, but it's not made up of atoms. It doesn't interact with radiation. And because we're looking at sound waves in the early universe, we can use that to say whatever it is has very weak interactions with radiation. We don't know what the dark matter is, but we can actually constrain a lot of its properties. And figuring out what the dark matter is one of the great challenges in physics, and one that I hope we'll make progress on in the coming years. We can measure how lumpy the universe is. What is the density of these fluctuations? And you can see it's a pretty small number. The typical fluctuation is about 1 part in 20,000 in the density of the universe back then. And those are the fluctuations that grow to form galaxies. And we can see that those fluctuations change with scale. This change in scale is small. It's nearly the same on all scales. And we've measured it with a much larger uncertainty. And the final number we measure to fit the data is how likely, we've talked about these photons traveling for 13.7 billion years to us. That's most of the story. About 90% of them do. About 10%, or to be precise, 8.8%, hit an electron on the way from long ago to us and scatter and produces kind of a polarized fuzz we see. That polarized fuzz tells us something must have freed that electron. Because remember, 380,000 years ago, we think all the electrons and protons combined to make hydrogen. Something freed that electron. Something heated up the gas. What did that? Well, a couple things that could have heated up the gas. Probably the best guess is stars, an early generation of star formation. But we don't know that for sure. It could have been an early generation of black holes where there was gas accreting onto the black holes. But we know from this number that the first objects must have formed about 400 million years after the Big Bang. So this kind of side measurement that WMAC makes actually is the best number we have that tell us when did the first objects form in the universe. About 480 million years ago they emerged. So now that we've taken the baby picture of the universe, we know what it looks like, and here's 3 randomly selected babies. We can evolve them forward in time to closer to today. And if you understand the early universe well, you can predict what they should look like today. Biology is much harder than physics. That's why I went into physics. Even if you have the biology down here, you really can't predict from the DNA what things will look like today. In physics, it's simple. We've got the DNA. We know what those microwave fluctuations look like 380,000 years after the Big Bang. That tells us how lumpy the universe was then. We can predict how lumpy the universe is today. And here's some measurements. And this is analysis done of this data for the Sloan Digital Sky Survey, led by one of my former graduate students Beth Reed, where we measure the amplitude of galaxy fluctuations versus length scale. This is an angular scale, but these are now length scales measured in each of these are measurements of millions of parsecs, or effectively millions of light years. So as we look as a function of length scale, these points say how lumpy the universe is today, just like our microwave background measurement said how lumpy it was back then. What's remarkable to me is this solid line here comes from taking what we see in WMAP, no free parameters effectively, running it forward in time, comparing to what we see in the galaxies. And the same model, the same parameters that fit what we see in the microwave sky fits the distribution of galaxies today. And the same pattern of plasma waves, or these acoustic fluctuations, seen in the C and B microwave background, also shows up, though with lower significance, in the distribution of galaxies. We call Baryon acoustic oscillations. And this consistency between what we see back then and what we see today shows up in lots of different sets of data. Back when I started out in this field, we had lots of different observations. We didn't know how to fit them together. They were pieces of the puzzle, and they didn't fit. Today, we have all these pieces, and they all seem to fit together. What's shown here are measurements of how bright supernovae are as a function of how far away they are, their redshift. And we don't need to worry about the details. What I want you to see is here's the data points from our colleagues who measure supernova data. This is a lot of the data associated actually with the Shaw Prize in 2006. And here, this black line is a model based only on the WMAP measurements. No free parameters. Comparing the two, they fit beautifully. The pieces fit together. There are many other pieces that fit together. Our colleagues using the Hubble telescope measure the expansion rate of the universe, the so-called Hubble constant. The value they get, the value we get, agrees to a few percent. One of my favorite measurements on this list is the measurement of the abundance of deuterium. Deuterium is a fossil. Almost all the deuterium in the universe was produced in the first 3 minutes of the Big Bang. So by measuring the abundance of deuterium, we can see what the universe looked like 3 minutes after the Big Bang. Astronomers studying quasars are incredibly bright, compact sources of radiation. We think they're supermassive black holes accreting gas. But for our purposes, we just care they're bright and star-like. They're like these brilliant flashlights out in space. They illuminate the gas along the line of sight. Optical astronomers measure the spectrum of these quasars, and they can measure the ratio of deuterium to hydrogen and measure the deuterium abundance. That gives them a measure of the density of atoms. Well, we have a measure of the density of atoms, those peak heights. Totally different physics. They agree to better than 5%. The pieces come together. So what do we have? What have we learned so far from our measurements in cosmology? We have this simple model that seems to fit the universe we see. It's a model that's strange and beautiful. It confirms the supernova evidence that we see the universe is accelerating. It also confirms a picture that really goes back to Jim Peebles' work that won the Shaw Prize in 2004, in which gravitational growth of fluctuations, these variations in density, grew to form the galaxies we see today. Where are we left in cosmology? In a very interesting place. We have a simple model that fits lots of data, but we're left with some really deep and profound questions. What is the dark matter? What is this dark energy? And perhaps the most profound question, how did the universe itself begin? So let me stop there. Thank you.